Over the past decade, theorists and experimentalists have found inspiration in nature as they have sought to unravel the physics, build mathematical frameworks, and develop materials and 3D and 4D printing techniques for structures that can change shape in response to external stimuli. However, complex multi-scale curvature has remained out of reach. Now, Harvard researchers have created the most complex shape-shifting structures to date, that is, lattices composed of multiple materials that grow or shrink in response to changes in temperature. To demonstrate their technique, the team printed flat lattices that shape mob into a frequency shifting antenna, or the face of pioneering mathematician Carl Friedrich Gauss in response to a change in temperature. To create complex and doubly curved shapes such as those found on a face, the team turned to a bilayer multimaterial lattice design. By printing materials with different thermal expansion behavior in predefined configurations, the researchers can control the growth and shrinkage of each individual rib of the lattice, which in turn gives rise to complex bending of the printed lattice both within and out of plane. The researchers used 4 different materials and programmed each rib of the lattice to change shape in response to a change in temperature. Using this method, they printed a shape-shifting patch antenna which can change resonant frequencies as it changes shape. To showcase the ability of the method to create a complex surface with multi-scale curvature, the researchers decided to print a human face. They chose the face of the 19th century mathematician Carl Friedrich Gauss. The researchers began with a 3D portrait of Gauss painted in 1840 and generated a 3D surface using an open source artificial intelligence algorithm. They then programmed the ribs in the different layers of the lattice to grow and shrink, mapping the curves of Gauss's face. This inverse design approach and multimaterial 4D printing method could be extended to other stimuli responsive materials and be used to create scalable, reversible, shape-shifting structures with unprecedented complexity. Applications areas include soft electronics, smart fabrics, tissue engineering, robotics, and beyond.